Thank you. All right. So let me start by asking a couple of questions. How many of you have seen Rainbow? All right, quite a few. So how about, how many of you have heard about, at least heard about green flash?
I've seen it.
Yes, okay, wow. Not many have. But how many have at least heard about it? How many have seen Pirates of the Caribbean? Okay, so there's a correlation. Yeah. So, yes, so both of those are, of course, examples of geometric optics phenomena. And I'm going to tell you what the green flash is. It's kind of cool. Right, and so basically the purpose of this talk today is to show how those geometric optics phenomena, and more precisely, like if you think of Rainbow or a few other examples I'm going to show you. So there are certain singularities that can appear in geometric optics. But as you know, light is super fast, right? So everything compared to light you can think of essentially static, or almost static. So what we're going to ask, what happens actually if you do start moving stuff around? So can these singularities change? How can they be modified? Okay, but before we start, just to see what I'm talking about, let me do. Right. So let me do a demonstration. Let's see if it works. Okay. So do you guys see this stuff happening on the ceiling?
Ooh, real demo.
That's pretty neat, right? Okay. So how many of you can explain why this stuff's happening? Alright. Okay, so here's another. So that was actually, it's a pretty unique artifact. That's a quark from a New York white wine Riesling.
Is your microphone on?
I'm not sure. Is this? Yes.
Yeah, okay.
Okay, so this is another artifact that's actually a cap from a mechanical pencil. So again, just to make a point, there's nothing amazing. It's not anything particularly special. And you see, like in this case in particular, that so as I move stuff around, so again, I'm not doing anything special, right? I just move the quark around, I can move the pointer around. So there are certain anomaly singularities. So okay, so there's a bright spot which is just laser, but when it refracts, you see some structures forming. Some of them are fairly singular, and those more singular structures, they're called caustics. Okay, so what we're going to basically try to see is what happens to those caustics as we start moving stuff around. So in the talk yesterday, it was kind of like thinking more about quantum mechanical systems. You drive them, what kind of new properties you can evoke. Even though I didn't emphasize yesterday, a lot of those phenomena do have their counterparts also in the classical realm. So you can replace cavities by harmonic oscillators like Boltzmann springs. You can replace spins by magnetic particles, and stuff still going to work. So today we're going to take it a step further, and then we're going to go into the realm of essentially, I don't know, 17th century physics, right? So geometric optics. And I'm going to try to see what can happen, again, as you start moving stuff around, as you start imposing some time dependence. Okay, so I promised the rainbow and the green flash, so let me at least explain how it works with rainbow. Please try to draw some pictures. I'm not sure if I'm going to be particularly successful, but okay. So here we go. So this will be a droplet of water, briefly spherical. So suppose the sun is going to be somewhere here. I mean, it's really far away, so so the light rays from the sun, they are essentially parallel. So when they hit the droplet, they refract somehow, then they bounce, then they come out. So similarly, okay, I cannot do Snell's law in my head, and I'm not very good at drawing, but let's do some reference lines. So the center ray obviously is just going to go in and out. Right, so that remains invariant. Okay, and now the only thing that we need to know is the following. So there's going to be a ray which goes kind of like all the way here, touches the droplets, and that will be essentially the angle of total internal refraction. So essentially it's going to dent in and going to do something and going to come out. And so my claim is that, so this collection of rays, each one of them is going to do something. It's going to come out on the other side somehow. But all of those rays are actually going to be confined in a certain sector, right? So essentially all of them are thought to be somewhere here. And in fact, you can show that in this region, there will be a region where there are two rays going through every point, and there will be a region where there are no rays whatsoever going through any point. So which means that the rays will have to kind of like sweep out and then sweep in. So they're going to be like a turning point. And just like, I mean, there are a bunch of analogies. Like this oscillator, the oscillator spends the most time at the turning point. So similarly here, as this kind of like bunch of rays sweeps out and in, there will be accumulation at a certain line, which of course, because of the spherical symmetry, axial symmetry, is going to become this kind of a cone where the light intensity is going to be the highest. Okay, so you're guaranteed to have this kind of special location with lower intensity going out and basically zero intensity over here. Now, as you know, the refraction coefficient depends on the wavelength. So, which means that basically those accumulation lines, they can be different for different colors, and therefore, yeah, we see if the sun is somewhere there, we see the rainbow somewhere over here. Okay, so this thing is an example of a quad. And what I was showing on the ceiling is also those kind of like bunching up those bright regions. They also call. Okay, that's the sort of nomenclature. Okay, so the green flash actually doesn't really have to do with caustics, from what I can tell. But let me tell you anyway how that works. Okay, so the green flash is something that you can sometimes see at the sunset. When the sun is setting, so it takes just a few minutes for it to drop down. But sometimes, so basically there are legends from the seamen that sometimes, like on a beautiful day when the horizon is nice and glass, you can see this green flash right before the sun disappears, right before the sunset. Okay. So how does that happen? So actually, this doesn't involve differential calculus or caustic, so maybe anyone can make a guess. So, and the disclaimer is that it is a true phenomenon. It's not some illusion. So, and we have a representative of the few who have actually seen the effect. And given that it was also in one of the key moments in the Pirates of the Caribbean when they went from the underworld to the overworld. I mean, you could imagine that it's also a sort of mythical phenomenon, but apparently not only. Could be a good PhD topic. Okay. Yeah. So the way it works, again, it's refraction, and it's the fact that there is a refraction works differently for different wavelengths, right? So imagine that you're sitting. Well, not imagine. You're sitting on Earth, right? That's our planet. So that's you. And so you observe the sunset. So it turns out that by the time you see the sun setting, actually the sun has actually disappeared, because we have the atmosphere, and the atmosphere is refracting light. Okay, I'm exaggerating, but okay, so the sun is going to be somewhere here, but you can still see. So even though, strictly speaking, if there wouldn't be any atmosphere, I mean, the sunset would be already long over. Okay. Now, the refraction, what it does is basically it splits the sun into several different suns. So this is where the sun actually is, and that's where you see it, right? By just continuing this rate. So the red sun apparently is refracting more strongly than the orange and green sun. So essentially, the green sun is setting the last compared to all the other wavelengths. And okay, so it also has to do obviously with the sensitivity of our eye, that we're sensitive to green as opposed to ultraviolet and stuff like that. But anyway, so that's that story. Okay, so as I said, this is unrelated, but it's just a cool phenomenon. And so I found out about reality of this phenomenon. Well, okay, I didn't think too much about it, but and I was affected by Pirates of the Caribbean from the lecture of Michael Berry a couple of months ago, I guess. And so I mean, all of you obviously use Berry phases and know about Michael Berry to some extent, but I encourage you to look up his papers and maybe even watch some of his talks, because they're really inspirational. I mean, they're really great, and sort of his credo, so to speak, is that okay, so we are all physicists, we do stuff, right? Some bit more complicated, some bit less, but there are a bunch of amazing physical phenomena just around us. Right, and it's basically the onus is on us to be able to understand them and to be able to explain them in a understandable fashion. And so he's definitely master of that. So yes, that was a question.
Yeah. So why don't we only see at the very end of the sunset then? Why don't we see this kind of like green halo around the sun during the entire time it's setting? If it's always kind of the green sun is always above the red sun.
Yeah. Okay, so for one thing, you should never look directly to the sun. But yeah, so in principle, you're right. So there should be a bit of an effect. Yeah. All right. So basically, there are two things that I'd like to tell you about today. So one is going to be, okay, first of all, caustics. How do they come about? Sort of the classical phenomenon. I mean, classical in the sense old. So then I'm going to tell you actually how that relates to what goes by the catch name of Catastrophe Theory. So this will be basically, first I'm going to tell you about the static ones, but then I'm going to tell you about some of them dynamic. So if the parameters of, let's say, of the medium and anything is function of time, what do you expect to get then? And so in the second part, I'd like to tell you about another phenomenon which I think has connection to multiple lasers and things like that, which I'm going to call, again, somewhat provocatively, photon accelerator. And there are a couple of different ways that I can think of that you can implement it. But what it's going to illustrate again is if you think of time as an extra dimension that you can actually do stuff with, you can sort of modulate parameters of your system as a function of time, then you can end up with pretty interesting singularities. So essentially you can pump up the energy of the photon or frequency of an individual photon essentially to, theoretically to arbitrarily high values. You can pump the energy density to, again, theoretically to infinite energy density, and also the energy itself can also be pumped to infinity, which should make you suspicious. But of course, in the end, things kind of like regularize out. So things are fine. So I suspect that the second part actually probably in some shape or form is known to the people doing nonlinear optics and lasers, but I'm not sure if it's known in this form, and okay, I'm not sure if it's known at all, but I will be happy to hear if somebody knows. Okay, so that's the plan. So let's start from the beginning. So how does the geometric optics work? Yeah, so suppose we have like a point A where there's some sort of source, and point B where we put a detector. So how do we figure out how light is going to kind of go from point A to point B? Okay, so we kind of know, like we told in school that the light travels in a straight line, right? But so where does that really come from? So is there a deeper reason behind it? Because I think in the end, of course, we know that the light is a wave, right? So something that people, I guess, didn't know a while ago. So there got to be some sort of physical principle that tells us that yes, the observable rays of light are moving in straight lines. So it turns out there is a variational principle behind it, and it's essentially the same stationary phase approximation that we often do when we solve saddle points, when we want to solve integrals by saddle point and so on. So essentially we consider like all kinds of possibilities, how the light can go from point A to point B. And the variational principle, which in this case goes by the name of Ivar Martin, says that in vacuum, the integral of time from point A to point B, so I'm kind of using notation here, it has to be minimal. So essentially the light wants to take the shortest path. And it is nothing in the end but the stationary phase approximation, because in vacuum we know that the frequency of light is not supposed to change. Well, in fact, if you don't change parameters of the medium as function of time, the frequency just doesn't change at all. So we can multiply that by frequency. And so what it really means is that...
Use the fat chalk, please.
Oh, yes. Okay. Yeah, so this is basically the variation of integral KdR or omega dt. So R is unfederated because it actually emphasizes that we're varying geometries. Okay, so another way to say that is, okay, so let's say we take this line integral, so we're looking at the difference of a phase at point B minus phase at point A, and again, right, and again. This thing, when we vary over possible trajectories, has to be theorem. And clearly that's going to select a straight line, the shortest path, and so the variation just means that we're kind of exploring some narrow bunch of paths around this straight line. All right. So the implicit assumption here is that the wavelength is actually quite short. If the wavelength is not particularly short, if we're dealing with long waves, of course, that loses sense. Okay. So now, suppose that we beef it up a bit, and suppose we are dealing with a distributed source. So let's say there is some sort of surface, and every point on the surface is an emitter. And in fact, let's assume that, say, each one of them is emitting in phase, which literally means that this thing is a wavefront. So this is a surface of a constant phase. So, and again, so let's ask, so how this, so let's say there's going to be some snapshot of this, of the phase front. How is this phase front going to evolve as a function of time? So again, let's put some point B here. And so now our requirement is going to be that again, so we essentially want to find points, separate points, which are going to satisfy this condition. Okay, to be more geometric about it, essentially I'm going to look for points which have the same distance from point B, right? So for instance, let's say this segment will send the light sort of in phase, so there will be this wavefront, and there will be an actual ray going out in that direction. So let's say this segment is going to send light in that direction. So really what this is a statement that A is grad phi. So essentially, if we have a wavefront, then the propagation direction of light is going to be given by the normal to the wavefront. And you can generalize it to high dimensions. All right. So the way to make it slightly more mathematical, suppose I basically parameterize this curve by, in this case, one-dimensional variable s. So it's basically some sort of arc length along this line. So what I want is this. Okay, so as I said, the phase here we're going to set to constant. Might as well set it to 0. They're going to be a phase at point B, which will depend on where it came from on the line. Right? So phase at point B, depending on where it came from. So essentially, the way to figure out, let's say if I fix point B, where the light came from, would be to take derivative of the phase. But now, so here it's kind of like next level of abstraction. I'm not going to mess with those curved trajectories. I'm going to say that, yeah, I know that from every point, the light is going to basically go in a straight line. So the only thing that I now need to figure out is among those rays, which ones are kind of going to come together. So basically, d phi ts has to be equal to 0. Okay, does this make sense? Yes.
So
if you just imagine that all of the little segments travel in a straight line,
Yeah.
and the ones that happen to be pointing toward B end up at B, how
Yeah.
do you account for interference?
So interference here is okay. So actually that's part of the point. That's so I guess you're going to see the answer to your question. I mean, so there are two aspects of it. So one is that the interference, of course, is the phase, right? So it's built into the phase. But here I'm kind of implicitly saying that okay, phase is a kind of like function of point B. But I did something slightly more careful because I said that I'm not just going to say that there is a phase which can be uniquely defined in every point. So essentially, I said that the phase also depends on where it came from on the surface. So that allows me to basically avoid issues with multi-valued functions. Because in general, indeed, multiple rays could come to point B, and each one of them is going to have its own phase, and that actually makes the phase function multi-valued. And that's in fact the key behind this caustic business, because what the caustics are, they are the surfaces in general in space, which separates the regions where you have multiple rays coming to the same point from the regions where you have, let's say, N1 or N2 different rays coming to the same point. So basically, there's got to be some sort of folding going on. So the interference is built into the rays here, but there isn't really. If you have rays coming from very different parts of the wavefront, you should really worry about interference. It's kind of like yeah. So many of those phenomena actually don't. Okay, so I should be careful here. So the caustics themselves, they take care of the interference perfectly, but if I look inside the regions where I have, let's say, multiple rays going in, I mean, these guys don't really interfere. And that's why you don't see anything exciting going on. It's only along the surfaces that there's sign fence. Okay? Any other questions? Yes?
I was just wondering about the frequency, if that's a separate thing, or like it's just a factor e to the I omega t which is carrying along with this phase front, or how should I think about it?
I'm not sure I get the question.
So I need not worry about the frequency of this wave front?
Yeah. So here I'm just assuming that the stuff is monochromatic at this point.
Okay.
So I'm just saying, yes, there is a wavefront. It has corresponds to a particular frequency light. So there is, let's say, the spacing between the peaks of the phase is going to be all the same. And I'm also not putting any medium in. I mean, you can do all of that, but let's not worry about it. Okay, so the story then with the rays goes as follows. So let me erase this for a second. Again, a geometry of it is very simple. So let's say if I want to figure out which parts of the front can contribute to the rays coming into the point B, I can basically just draw a bunch of concentric circles and see where those circles are going to touch the wavefront, the surface. So for instance, one big circle is going to go through here, another one is probably going to go through there, another one I'm going to go through here somehow, right? And so each one of them is going to contribute a ray going through point B. Like, so for this kind of wavefront in the past, I know that there will be 3 rays actually going through the point B. Okay. So there are some cases where the calculations are actually particularly straightforward. So let's do that. Yeah, so suppose we have, I'm going to change a little bit the orientation of the geometry. So suppose we have the wavefront, which is parameterized by the height function. So this is our, let's say, x, and we're doing it in 1D. which means that all our geometry is going to be 2D, but you can generalize it to higher dimensions. Okay, so again, the same game. So we have this wavefront. It wants to propagate in the directions which are sort of normal to it. And so now we want to ask, so suppose we put a screen at some height z. So we want to see, what kind of light is going to be coming into the screen. Okay, so where it would be coming from. So this minimal phase principle, the Fermat principle, tells us that we basically, okay, so now this is our coordinate x, and we want to calculate the phase difference between the point here and the point there. So it's going to call this point x prime. This is going to be point x f of x. And so now let's do just a little bit of algebra and differentiation. Okay, so this distance obviously is what? Is a square root of z minus f of x squared plus x prime minus x squared, right? And that's the distance. So this is going to be our 5b of x. Okay, so then using this equation that I erased over there, the rays are going to be defined by the equation, by the condition d phi x dx equals to 0. Right. So what does it give us? F prime over the square root minus z like that. Make sense? Okay. So, okay, so now you can basically play different ways. The simple one would be say, okay, so this function of x, right? I mean, all of that function of x. So I'm going to kind of like reverse the problem. I'm going to say, okay, I'm going to pick a point here on this line. I'm going to try to figure out where going to be the sort of the ray intersection with the plane at height. So basically I'm going to express x prime in terms of x. And so you see immediately that x prime is going to be x plus f prime z minus f. Okay, so the so-called Praxel approximation is when f is much smaller than z, so I can basically drop this f over here. Or x, yeah. I think that's how you spell it. So you just get x plus f prime z, and I think I screwed up sign somewhere. Right? I did, yes. Because I should not have flipped sign here. So minus sign. Okay, and this is totally expected because, so f prime is just the slope, right? So here slope is negative, but the ray is going to be going in the positive direction, and the distance is going to go is basically the slope times the height, so just some tangent. Okay, so that's expected. But now suppose we are looking for some singularity, some anomaly. So we want to have more than one ray going, let's say, to a particular point, right? So that means that, in fact, not only the first derivative, we basically have to go to higher derivatives. We want to basically get more light from a certain region of space which really boils down to taking yet another derivative over x and requiring that that it's equal to 0. Okay, so if you do that, I'm not going to bore you with the derivation. What you get is the following. So it's minus z f double prime plus 1. So essentially that condition boils down to z equal to 1 over f double prime, which is again expected because that's basically a curvature of this line. And so you know that if I have, let's say, spherical front, I know for sure that it's going to basically go into the single point. So that's what this thing is telling you. Okay, so now let's do something fun with this. But before we go, so question. There's a somber mood. Like, why is he telling us all this geometric optics? Okay, cool. All right, so this is fairly general. Let us look at something specific. And so that's how we can get to those things on the ceiling. So suppose we take f of x, which is x squared plus c x to the 4th. In fact, okay, so let me make it slightly more general. So, and coefficient here, to simplify notation, put 1/2 here, put 1/4 here, because we'll have to take some derivatives. Okay, so what are these equations going to give us? Okay, so first of all, we're going to find that for this particular example, okay, be consistent with my notation here, not to get confused, so let's put b. So x prime is going to be x right minus ax plus bx cubed. Okay, so and then we add basically z over there, right? But at the same time, I know that z is one of the second derivatives, so I can just stick it in. So it's going to be okay. So we can simplify that. You see that ax cancels out, and we get only some higher order in x. Okay, so that's result number 1, and so let's use again that z is equal to 1 over a plus 3 bx squared. Okay, so essentially this is the equation in the coordinate x prime and z, which tells us where are going to be interesting points. So where is going to be accumulation of intensity. Okay, and so let's expand this. Okay, so what it tells you is that the plane, sort of the focal plane, is going to be at a distance of 1 over the curvature, roughly. But then, so it's going to kind of like fan out a bit. So something is going to happen as a function of of x. But what we care about is the dependence of z on x prime. So let me substitute, instead of having x, I'm going to substitute the cubic root of x prime. Right, so essentially this becomes 1 over a, which is a constant, minus 3b over a x prime and to the power 2/3. Okay. So if I now plot this function, and I should have done it there on top of this face round, but that's okay. Let me redraw it. So what this thing is telling me is that so z as a function of x prime is going to be this pretty singular function. So if b is positive, it's going to be tilting down like this. And if b is negative, it's going to be doing. So these are two different cases. It's going to be doing something like that. Okay. So you get this what's called cusp singularity. Okay. And so you see, it's okay. It may not be totally obvious that it's anything particularly universal, but it is. And I'm going to show you next why. But let's look back at this guy. Yeah. So if you look carefully, so you see those. Okay, maybe here in particular. Yeah, you see this. Okay, so there's some interference ranges and stuff, but let's ignore them. So you see this cuspy thing, kind of like this nose sticking out, right? And that's an illustration of this phenomenon. So the reason it happens is precisely because we have this extra, like little correction to the shape. So if we have just x squares, everything would get focused at that point. But because, let's say, our mirror is not perfect, the focal point is going to smear out, and it's going to smear out in this very nice and universal fashion. All right. So, questions here? Okay. So what does it have to do with catastrophes? And so I recommend very strongly there is a paper. Let me give you the reference. So it's Berry and Upstill. In Progress in Optics. And so basically, Barry actually has all his articles, all the PDFs on his website. You can just go there and download whatever you like. So this one has basically, I forget the precise title, has catastrophes, geometric catastrophes, solved catastrophes in the title. Okay. So okay. So catastrophes. Okay, we're not going to get to the second part, but that's right. Yeah, so the catastrophe theory, I mean, it has this dramatic name, and it seems like it's one of those examples where musicians were having too much fun. So you read the papers of the guy who really advanced both the term and the field is the field medalist René Thon. And I mean, it's okay. I cannot be a judge, of course, but it's a very important, very respected work which has a lot of follow-up. But the guy also went a bit far trying to apply this catastrophe theory to everything, like why dogs bite, or why do you need to agitate them long enough to bite you, and like why creative people become alcoholics. I mean, all kinds of stuff. But beside the point, so there are multiple ways to think of the catastrophe theory, and I think the original one was in the context of maps of two-dimensional surfaces on the plane. So example would be projection. So you take, let's say, a cylinder and you project it onto a plane. So typically you have like point from the top projects on the bottom, point from the lower part projects onto the surface. But then near the edges, you get those singular projections, which have some anomalies. I think sort of more intuitive way, which I think is also more common way, is to think in terms of the extremal points of functions. And let me illustrate in terms of 1D, and hopefully you're going to see the connection with that story. So suppose we have a function f of x, and okay, so what are the examples? Okay. Linear function doesn't have any extremal points or stationary points defined as. You can have parabolas, then they have one extremum. You can have cubic parabolas, two extrema, and anything in between. The polynomials are important because, as you know, essentially any smooth enough function can be expanded in polynomials in some vicinity. So it is sufficient to think about polynomials to a large extent. Okay, so catastrophe theory basically asks the question. So what is the natural, or what are the possible types of evolution of the extremal points as I change parameters of my system? Okay, so for instance, if I take to be specific, the first non-trivial case, say ax squared plus bx plus c, and I start varying the parameters, a, b, c, clearly nothing much is going to happen. If I vary c, the function just moves up and down. The points of extremum doesn't move at all. If I change b, okay, I change the tilt, so the minimum is going to move left and right, but again, nothing special happens. If I change x, nothing happens at all, essentially. Okay, so this is a vegetable. And the vegetables go by they have a term for them. They're the Morse functions. They're the functions which have the form locally of ax squared. So that's the highest power that's present in these functions. Okay, so the cubic parabola is already more interesting, as you can tell. So say we have x cubed plus dx squared plus cx plus d, right, most generally. Because these guys can be either this shape, or they can be of this shape, where the two extrema fuse together, or you can completely eliminate the extrema. Right, and all of that will happen as a function of the parameters. So basically, as it turns out, this is basically one of the examples of what the catastrophe theory studies. It studies those higher order extrema and how they can be unfolded, how they can be broken up. So this guy obviously is x cubed, minus x cubed if you like. And then the question is, if I start adding extra terms, let's say quadratic, linear, well, constant obviously doesn't do anything. So how this high order singularity breaks apart. Okay, so this is a very simple example. We can work it out. So what you do is just that equals to 0, which means that 3 squared plus dx plus c equals to 0. So you all know what I need to do. I need to find the discriminant, and if the discriminant is positive, then there are two roots. If the discriminant is negative, then there are no roots. And these are really the two cases. So d greater than 0, d less than 0, this is d equals to 0. Okay, so there is really not much about this. In fact, let me do another simplification which will really make it trivial. So clearly by making a shift in the x, I can eliminate the quadratic term at the cost of modifying the linear term. So actually this one is not particularly important. And then you see that if I just have this kind of cubic parabola x cubed plus cx, if c, okay, I should really be consistent with a minus sign here. So if c is positive, then I'm going in that direction. If c is negative, I'm going in that direction. So essentially, I have a non-trivial single parameter space, C, and so for C negative, I have 0 solutions, and here I have 2 extremal solutions. So essentially, it's the counting game. Yes?
So are you studying the value of the function at the extremal points, or the value of the extremal points?
Just the existence, like how many extremal points you have.
So
Okay.
is this like, isn't this like the same thing as people talking about like bifurcations in dynamical systems?
It's closely related, yes. Yeah, exactly. Okay, so the second example I'm going to give you, and then we'll have to stop, is, so I really didn't get past this, I'm sorry. If there are questions, I'll be happy to discuss separately. So suppose we have a function which is next higher order. So this is going to be f of x, x fourth, minus dx squared, minus dx. Okay. So again, I'm dropping x cubed because I can eliminate whatever x cubed term I put here. I can eliminate by shifting the origin by going to x plus c. Okay. All right. So again, so the name of the game is, do we want to figure out this function, how many extrema it's going to have? So of course, all of us study second order phase transitions and such in a field or without field, so we know how this function looks like. So x to the fourth is going to be just somewhat flattish parabola. If b is positive, then we just have another positive. Sorry, if b is negative, then we have yet another contribution, so we have just one minimum. But if b is positive, then we start getting other two minima. So now instead of having one extremal point, we're going to have 3. And now if we start putting in some c, that's going to introduce some tilt in this overall shape. And you can sort of see that if c is big enough, then instead of having 3 extremal points, I'm going to end up having again just 1. Okay? So let us see how that happens. So that's one condition. So essentially, the extremal points satisfy this equation, and the way you should think about this is that this equation is really what specifies the yeah. So it's basically it's a function of x, b, and c. So it defines a certain surface, And now we're going to analyze what are the properties of this surface, meaning how many essentially x solutions for a given set of B and C we have. So the easiest way to do that is to say that, okay, let me just say that C is equal to 4x cubed minus 2bx. Let's draw it. So this is going to be our C. This is going to be our x. And this is going to be b. So if b is equal to 0, we have this. So we are essentially sitting in the in the xc plane. We're going to have this kind of cubic parabola. I'm not sure if it's clear. So basically, this line sits in the xc plane for b equal to 0. If b is now going to move into negative direction, then just like in the previous case, we get a flatter situation. So we it gets somewhat messy here. Okay, so the simple point is that if b becomes negative, then we just have a single value of x, because now so this is not a very good 3D drawing, but what it's supposed to convey is that for b negative, you're only going to have one solution of x. I mean, there's only one value of x for which basically a vertical x-axis intersects the surface. Okay, that's, I'm sorry, I think I lost you all. Yes.
So where in this structure is the universality?
Yes, you'll see it in a second. Okay, so because you'll see the universality, and you're going to see this power 3/2, 2/3 popping up in just a second. Because, okay, so for B negative, we have just, I should have brought some picture, which is not as hard to understand. Okay, so if you go to B positives, you get this kind of fold in the shape of the surface. Okay, so let's maybe reload. Okay, so we have a three-dimensional space, x, b, and c. Okay, so now this equation is an equation for a surface in this three-dimensional space, right? And now we want to see for fixed parameters b and c how many x solutions this thing has, right? So fixing b and c means that in this b and c plane, I pick a point, right? And then I see basically at this point how many x solutions do I have, essentially how many intersection points I have, okay? So even though this picture is messy, please trust me that for b less than 0, there will be one solution, one x solution. And for b greater than 0, there can be either 3 or one solution. So 3 solutions is when this vertical x line is going to intersect the surface in 3 points, and there will be one solution when it intersects only in 1. Okay. And now the question is, so what is the curve in the BC plane where I go from one solution to 3 solutions? And the connection that you might begin to see with this geometric situation is that there as well, within the cusp, you have 3 phase solutions, 3 possible phases that you could have, and outside there is only one possible phase. And the correspondence is not coincidental because, so here we're looking at the maximum of some abstract function. So but there as well, we were looking at the, well, not necessarily maximum, extrema of some abstract function. So there we're looking at the extrema of the phase. Because the extrema of the phase, they correspond to basically directions of propagation. They correspond to the rates in geometric optics. Okay, so how does this universality business come up? So that's a good exercise. And, since I'm out of time, I'm not going to impose it on you here, but you can do it separately. So you basically need to figure out where the position of this fold in the BC plane goes. And what you'll discover is that the fold actually forms this kind of custody structure. So essentially, if you just project this surface with a fold, maybe you can do it with paper, but probably not, you're going to see that the fold actually naturally forms this 2/3 and only in the plane. Okay.
So Ivar, I mean, you know, that was cool, and it's nice to be able to explain it, to understand it, you know, all analytically. But is there a reason why we should care about this beyond pretty projection on the screen?
I think there might be a reason to care. Yeah.
What is that? What are they?
Yeah. So yeah. So one thing is that okay. So this is a big effect, right? All those caustics are singularities, and the classification of singularities, as it turns out, is as topological as many of the other things that we're trying to do. Now.
So you're saying these caustics and the singularities have something to do with the blockade thing we were discussing yesterday, or topologically some different?
So yeah, I didn't get to that point, and I should have anticipated.
Can you make the
that.
point in
But,
20 seconds?
Yeah, right. Seems to be like a motif of my talks. Yeah. So the point here is that yes, Now, so this was a static picture, but you can also make it dynamical. Okay, so there are a couple of ways. So one, you can make, for example, your wavefronts, which, okay, if you want like more kind of like particle, maybe not quite condensed matter, but particle-like picture. So the fronts, so the wavefunctions for the photons, are going to be modulated somehow. So for instance, you can imagine having some sort of mirror and you modulate the shape of the mirror. So what happens then, it turns out that the types of anomalies that you can get gets richer. So that's one thing. Okay, so the other thing, but this is kind of just a general statement. The thing which is more closely related to the Flequet stuff that I was telling you about before is that, so Flequet, as you know, works pretty well for simple Hamiltonians, right? A single body Pauli matrix at best. Is the best, even though it's not the most interesting case. So the question is what you do when you have systems with more degrees of freedom, right? And so the simplest example of system with more degrees of freedom is a field, let's say harmonic field, right?
Harmonic what?
Harmonic field. So it's basically a field of harmonic oscillators. So that could be, okay. So there are two simple cases. One is free fermions, the other is free bosons. Okay, so I take free bosons. So it turns out that if you start modulating free bosons, and you can imagine doing this, for example, by taking a cavity and modulating the separation between the mirrors. It turns out that because of the distributed nature and because you have more degrees of freedom, you can start generating basically singularities of this type, but somewhat more general, where you get like huge peaks in the energy density and so on. So it's still, in a way, non-interacting physics, but these are the cases where actually you can go through, I mean, using fairly simple pictures, simple calculations, you can go through and get results which are, I think, physically quite interesting and potentially even useful.
So the point is, if you try to do flow K with more than one, say, Howell matrix, this is going to become relevant?
Well, I'm not claiming it's going to be relevant everywhere, but for some problems, like is relevant, say, for optical fields in the cavities. Yeah. Indeed. Yeah, and yeah, I'm sorry it didn't. It fits into the actual allotted time, but yeah, if it sounds marginally interesting, I'll be happy to discuss everything.
Excellent. Let's thank Ivar. Do we have any other questions?
I'm trying to distill it, and that if I just had a mirror, say, and I'm reflecting light from it, I'll get a Doppler shift. So would that be an example of what you're talking about as I go through a sinusoidally modulated mirror?
Yeah.
That the density.
Yeah. So I can draw a picture, and so that will be this thing. Yeah. So suppose you have two mirrors. So one stationary. Okay. So this will be our time dimension, and this will be the x dimension. So let's say one mirror is just fixed in space, and the other mirror is doing something like this, right? Modulated. So now suppose we make some sort of wave factors, right? So the wave factor is going to be moving with the speed of light. It's going to bounce off. So this is also a mirror. I'm going to bounce off again. Okay, so the thing which is actually kind of trivial, embarrassingly trivial, you can show that, okay, so the slope here is the velocity of the mirror. Right? That on every bounce, basically you get the shrinking of the wavelength, but in fact it's more than that. So the whole wave packet basically just uniformly shrinks. So you get this here, then it bounces back. Like that, so it's basically state direction propagation. Basically, after every bounce from the mirror, you get the Doppler, which is like that, right? And it keeps going. So essentially, if you put your mirror in the resonance with the I mean, not even precisely resonance, but it's a close enough resonance with the travel time back and forth. Your k grows, so essentially your frequency grows. But in fact, it also means that the energy density grows as square of that, and the energy grows as linearly with that. Yeah. So you get this fairly bizarre situation where, I mean, it's exponential, right? So your wave packet's size shrinks exponentially, and the energy grows exponentially. So it's pretty strange phenomenon.
Yeah.
Have you heard about it?
It's a pulse compressor.
Yeah, some of those. I read about a little bit about the small block lasers, and something like this seems to happen there. But and of course, in reality, you have to worry about all kinds of operations and non-idealities and so on. But yeah, so this is going back to Una's question. That's one example of singularity that you get in this kind of driven system, which I don't think you can get in a static, kind of like canonical caustic systems.
Any other questions?
I don't understand where in what you just described, where the catastrophe theory comes in as a description.
Yeah, so here actually I don't know either. so I think it's somewhat different phenomenon. It's a similar in some spirit. Okay, so the catastrophe thing, if you want, I can tell you separately. So there the point was that if I change parameters of my wavefront, so let's say it's a mirror that's bouncing lights, and I change the shape of the mirror. So there, indeed, the catastrophes come in, and I can show you what happens. So you get sort of like colored catastrophes, and instead of cusps, you can get other types of singularities. I'm not sure if they truly fall outside the standard classification. I doubt, but I don't know yet how they precisely fit.
Okay, let's thank you very much.